Hello everyone, my name is Ekin Bircan Boşdurmaz and this is my EEE 414 Introduction to CMOS VLSI Design Term Project video. We are asked to design a serial 64-bit digital correlator which has a serial input and which has three output pins named as sync no, and data polarity. The data polarity output pin is detecting which data is inverted or not. Sync now is detecting that, signaling that which synchronization pattern is matched from the incoming data, and sync determines that which pattern is detected within a programmed error rate. We also can program this 64-bit correlator from its program input pin, which we give two 64-bit synchronization patterns and 5 bits of allowed error. You can see the block diagram of the correlator from the screen now. We have, as we said before, we have 5 input pins and 3 output pins. And basic operation is like given in the following schematic. From this, we wrote a VHDL code that can prescribe the behavior of the schematic, and you can see the synthesized schematic from the Vivado software. We have like regular design, we have input side, output side, and the middle we have like this adders and multiplexer. For that, we also use the Vivado software for behavior simulation to check that our design is working or not. As you can see, we have a sync pulses, and we also see that it can also generate sync pulses while it can be programmed, while it is programmed. Also, after that steps, we went to the second part of the project to synthesize the gate level Verilog file from the VHDL code using Janus, and also perform the placement and routing and clock tree optimization of the design from using Innovus. Before that, we use a table to find out which voltage is the best for our design, and we found that our best performance is achieved by 2.2 volts with the minimum energy delay product. Also in this here, you can see that the setup time and power information from Innovus, and you see that also we have the best performance for 2.2 volts and the total array of the design. You can see that the routed clock line before the clock tree optimization is the left side, which has significant amount of delay, and the routed and the optimized clock line on the right side, which has like reduced delay. Also, you can see the layout from both Innovus and Virtuoso software. After that, we go to the part 3 of this project to make our design testable. We update the previous files to make the correlated design testability and adding 3 pins and generate the test patterns for the post-production test using Modus, and also we redo the placement and routing to compare the setup timing and power with the previous design. You can see that from this slide now, we have this 96% of AT coverage, and you can see that Modus has generated with no errors, 0 miscomparing vectors, and we also tried some stuck at 0 and stuck at 1 errors. You also see that from adding the design for testability feature, we increased our area and also the power requirements. And also you can see that our clock period is increased from 30 nanoseconds to 150 nanoseconds. You can see that final layout of these chips from Virtuoso software and Innovus software from here. Thanks for watching, and you can find the VHDL code and project documentation from this link. Thank you for watching.